Hi everybody, this is Arif. Today we will talk about Laplace Transform. It is a really important mathematical tool that we use a lot in physics and engineering, especially when we want to solve differential equations. So we will learn all the basics about Laplace Transform today. We will also do some derivations and we will look at the properties of Laplace Transform, so forth and so forth. And in the end, if we have time, we will actually solve a problem and we will see how it's actually applied in a given example. So before that, let's talk a little bit about Laplace. So Pierre-Simon Laplace was a French scientist who lived in second half of 1700s and early 1800s. He was a great scientist, and some actually consider him as Newton of France, or the French Newton. He had a vast knowledge on almost everything of his time. His work actually was so important to the development of physics, engineering, mathematics, statistics, cosmology, astronomy, and even philosophy. So I strongly recommend that you go ahead and read about him, learn more about him, and he was an amazing guy. So what is Laplace Transform? The definition is straightforward. So the Laplace transform of a function, it is an operation acting on a function f of t. So it's defined as an integral from 0 to infinity e to the minus st f of t dt. Okay? Of course, when we see an integral like that, the first question that we ask is whether this integral converges. Okay? It's a big question. So since this is an introductory level course, we are going to assume that the integrals that we discussed today are all convergent. So we don't see any crazy stuff going on. In other words, Laplace transform of a function exists. So this is what we are going to assume. So in simple terms, okay, this s is usually a complex number, but for the sake of simplicity, we're just going to assume it is real. Okay, and in simple terms, the convergence or the existence of this Laplace transform is ensured if we can find an s naught, okay, e to the minus s naught t, such that okay, this whole thing is bounded. So it's like a finite number here. So if we can find an s naught which satisfies this condition, then for any choice for s, so if it's a complex number, this is just the real part, but if it's a real number, we just use it as is. So then for any choice of s larger than s naught, which is larger than 0, this Laplace transform exists. Okay? So as I said, we will not worry much about the existence of the Laplace transform today. We will just assume it exists and we will try to derive the relations and come up with the Laplace transform of different functions, so forth and so forth. So here the next question is, what is this f of t? Okay, f of t. So since we'll be mostly solving physics and engineering problems, this f of t is in general our physical observable, okay? It's our measured quantities. So we assume that f of t is defined for t larger than 0. What does that mean from the physics point of view? So if we are running an experiment, okay, we start our timer at t is equal to 0, okay? And then we start observing our physical variable. So what can it be? It could be like current in the circuit, charge on the capacitor, or the position of an oscillator, okay, or temperature in the room, so forth and so forth. So it may be anything that's observable. Before we move on any further, I would like to talk about a terminology here. Due to its resemblance to Fourier transform, sometimes this S is called frequency. Okay? So what this Laplace transform does is takes a function in t space, if it's time, so it takes a function from the time domain and transforms into another function in the frequency domain. So this is nothing but another function which depends on S, right? So in doing Laplace transform, we go from time domain to the frequency domain. In other words, from t space to S space. So the very first thing we observe in this definition is that the Laplace transform is a linear operation, right? So the Laplace transform of C1 f of t plus C2 g of t is simply equal to C1 f of s plus C2 g of s. So here C1 and C2 are two constants, and f of s is the Laplace transform of f of t. So the Laplace transform of f of t is defined as f of s, and the Laplace transform of g of t is simply equal to g of s. Okay. So we will be using this linearity property in solving some of the problems. Now we are all ready to find the Laplace transform of various functions, look at different properties, derive some relations, so forth and so forth. So it's going to be so much fun in the next 50 minutes maybe. Please go grab some coffee and tea, pause the video, get relaxed, and just enjoy the ride. Now we will find the Laplace transform of 1. It's our first example. It's the easiest one, right? So it's nothing but from 0 to infinity. I'm going to use the definition here, e to the minus st dt. So this is nothing but minus 1 over s e to the minus st. The limits are 0 to infinity. So this is simply 1 over s. And we require that s must be larger than 0, right? Okay, so Laplace transform of 1 is 1 over s. Next example, what is the Laplace transform of e to the kt? Okay, so it's going to be e to the minus st times e to the kt dt. But this is equal to 0 to infinity e to the minus s minus k t dt, right? This integral is similar to that, but instead of s, I have s minus k. So this is minus 1 over s minus k, requiring that s is larger than k. Otherwise, the integral diverges, right? So we have a stricter bound here, lower bound, for the s parameter. Okay. So we are done with these two functions. First, I'm going to do the hyperbolic cosine and hyperbolic sine functions, and then we will continue. Our next step is to find the Laplace transform of cosine hyperbolic. So I already got 1 and e to the kt. Okay, so this is nothing but Laplace transform of e to the kt plus e to the minus kt over 2. The definition of cosine hyperbolic, right? So I'm going to use the linearity property and Laplace transform of e to the kt. So this is nothing but 1/2 parentheses. This gives me 1 over s minus k plus 1 over s plus k. So if I equate the denominators here, in the end what I get is I'll have 2s up here and then 2 cancels, s over s squared minus k squared. This is good. Similarly, what is sine hyperbolic? So instead of plus, I'll have minus here, and this would bring me 2k up here. 2 divided by 2 is 1. So this is nothing but k over s squared minus k squared. Okay? This is good. So now we can look at sine and cosine functions. So what is Laplace transform of cosine kt? Okay. So this is going to be Laplace transform of cosine hyperbolic. I hope you all remember that I kt, right? What is I? So I squared is equal to minus 1. This is my imaginary I, right? So this is going to be equal to, wherever I see k, right, I'm going to put ik. So I squared is minus 1. It's nothing but s over s squared plus k squared. Most of the time, when we have a cosine function like that, okay, instead of k, we are using omega, right? So I'm just going to rename it, relabel it. So this is omega, this is omega, this is omega, okay? It's just using a different name, right? You can call it X, Y, Z, T. We already used T, sorry. We can use whatever we like that to be. But by convention, we are using omega, okay? And this is the angular frequency, of course. How about the sine function? So similarly, I'm going to use omega here due to the convention. Sine omega t. So it's going to be equal to the Laplace transform of, I hope you remember this one too, minus I sine hyperbolic I omega t. So not only replacing k here with I omega, but we also need to put minus I in front. Okay, minus I. So wherever I see k, I'm going to put I omega for the sine function. So this gives me I omega up here divided by s squared plus omega squared. Okay. So I times I is minus 1. This cancels this minus 1. So up here I just have omega. So far we have found the Laplace transform of hyperbolic and trigonometric functions. Now we will continue with some more. Our next goal is now to find the Laplace transform of t to the n. So I'm going to assume n is a positive integer. Like 1, 2, 3, 4, 5, 6, 7, 8, it goes on like that. So n is a positive integer. So this is equal to 0 to infinity e to the minus st t to the n dt. Okay, so let's use integration by parts, right? So u is equal to t to the n. So I'm going to drop this power, right? I'm trying to reduce that power. So that's why I pick u to be t to the n. So du is going to be equal to n times t to the n minus 1. Right? You see, I reduced it by 1 dt. Okay. How about dv? So I'm going to pick dv as e to the minus st times dt. So v becomes minus 1 over s e to the minus st. Good. So this integral becomes u times v minus 1 over s t to the n e to the minus st minus v times du. So I have 1 over s here. Minus becomes plus. Then I have n here. It's a positive constant. And then this integral is 0 to infinity e to the minus st t to the n minus 1 dt. Okay. And the limits of the first term is from 0 to infinity. So as we see, when t is 0, this term is 0. When t goes to infinity, this term is 0, e to the minus st term. And basically, this term is 0. So we end up with this integral here. Okay. N over s and that. Okay. So if we apply one more integration by parts. So u is now t to the n minus 1. So du becomes n minus 1 t to the n minus 2 dt. And then dv is going to be again e to the minus st dt. So v is equal to minus 1 over s e to the minus st. I hope you are all with me. Okay, so this gives me n over s was already here, parentheses, u times v. So minus 1 over s, right? T to the n minus 1, okay, times e to the minus st, 0 to infinity, then minus v times du. So I have n minus 1 over s here. So it becomes plus n minus 1 over s integral from 0 to infinity e to the minus st times t to the power n minus 2 dt. Okay. At this point, we also see that this term is 0. Okay. And what we get is, let me rewrite it. So n times n minus 1 over s squared, right? Integral from 0 to infinity e to the minus st t to the n minus 2 dt. Okay. So we applied the integration by parts twice, right? And in the end, I get here t to the n minus 2. So if I apply this like n times, right? What are we going to get? So here in the front, we're going to get n times n minus 1 times n minus 2 times n minus 3. It's going to go like that. This power is going to reduce by 1 each time I apply the integration by parts. So this is going to go all the way to 1. Okay? So the Laplace transform of t to the n is going to be equal to, up here, I'm going to have n factorial divided by, here, I'm going to get s to the n. Okay? And the integral would be, after applying n times, right, integration by parts, this is going to be n minus n. So e to the minus st dt, 0 to infinity. But what is that? This is the Laplace transform of 1. We already know what it is. It's 1 over s, right? Okay, I can simply put it here then, n plus 1. So this is the Laplace transform of t to the n. N factorial divided by s to the power n plus 1. This was a good one. So let's continue from here. Next, we will discuss frequency shifting. Okay. Let's suppose the Laplace transform of f of t is equal to f of s. Okay? So let's find f. So if I shift this frequency, right? This is s here. So if I introduce a positive a, so if I call it s minus a, okay? What do I get is e to the minus s minus a t f of t dt. 0 to infinity, right? Okay, so I can write it in a little bit different way. Okay, so it's going to be 0 to infinity e to the minus st times e to the at f of t dt. So you see, I have a function in front of e to the minus st as e to the at times f of t. But this is nothing but, this whole thing here is nothing but the Laplace transform of e to the at f of t. So if f of s is the Laplace transform of f of t, f of s minus a, okay, it's going to be the Laplace transform of e to the at times ft. And this is called frequency shifting. Okay? And next, we are going to talk about time shifting. So we are done with frequency shifting property, and now we are going to do time shifting. So if you shift the time, right, this is what it means. So Laplace of f of t minus a, this is what I'm trying to find. So here I assume a is a positive time. A is positive here. So this means that, as you may remember, f of t was defined for t larger than 0. So in this case, f of t minus a is going to be defined for t larger than a. So the Laplace transform of this is going to be equal to integral from a to infinity e to the minus st f of t minus a dt. This is good. So at this point I can make a u substitution. So u is equal to t minus a. du is going to be equal to dt. Okay. So this integral becomes, when t is equal to a, u is equal to 0, and the upper limit is still infinite. It's going to be equal to minus s. Instead of t, I'm going to put u plus a, right? And then f of t minus a is u, dt is equal to du. Okay, so this is the integral I got. E to the minus sa is a constant, right? So there is no u dependence there. So this is going to be equal to e to the minus sa. So I just put it out. The integral from 0 to infinity, e to the minus su fu du. So as you see, u is my dummy variable here, integration variable. So I can simply call it u or t, whatever I like. In the end, this integral is nothing but the Laplace transform of f. So you can call it f of s. So the Laplace transform of f of t minus a, where a is greater than 0. Okay, the Laplace transform of this is nothing but e to the minus sa times the Laplace transform of the function f of t. Okay, so this is good. So now we will move on with some other nice properties. So next property is the time scaling. So I want to find the Laplace transform of f of a t. So again, a is a positive constant here. Okay, so this is going to be equal to, from 0 to infinity, e to the minus st f of a t dt. So I can call u is equal to a times t, then du is simply equal to a times dt. Okay, and then this integral becomes, so dt is 1 over a du, so I have 1 over a here. So the integral becomes 0 to infinity. The limits don't change. I will have e to the minus s. So instead of t, I'm going to write u over a times f of u du. Okay. So this becomes 1 over a integral from 0 to infinity e to the minus. So instead of u over a, I'm going to write it as s over a. So now this is s over a u. Okay? F of u du. Here I can simply call this s over a as s prime. So this is another frequency parameter, right? So this becomes 1 over a times, this is nothing but f of s prime, right? So s prime is defined as s over a. So this is equal to 1 over a f of s over a. So if we have a scaling like this in the t space, in the frequency space, this is going to be the Laplace transform. Okay. Here, f of s is of course the Laplace transform of f of t. Okay. And this is also another nice property. Okay, let's move on with the derivatives and other fancy stuff. Next step is to do the s space derivative. So what do we mean by that? We already know that f of s is equal to 0 to infinity e to the minus st f of t dt. This is the standard definition of the Laplace transform. Okay, so now I want to take the derivative of f with respect to s. Okay, this is a function of s. The limits here are not functions of s. Okay, so I just need to take the partial derivative of inside here. 0 to infinity. This would bring me minus t, e to the minus st, f of t dt. Okay. Okay, so then if I take the next derivative, it's going to bring me another minus t here. It's going to be minus t to the power 2. Then in general, if I take the nth derivative with respect to s, what I'm going to get is integral from 0 to infinity e to the minus st minus t to the power n, right? F of t dt. Okay. Well, this can be written in a little bit nicer way. So there is minus 1 to the power n here. I can take that out from 0 to infinity, right? To the minus st, t to the n, f of t dt. And this is nothing but e minus 1 to the power n, okay? And the Laplace transform of t to the n f of t. Okay? So the nth derivative of this function f with respect to s, okay, is simply equal to minus 1 to the n, the Laplace transform of t to the n times f of t. Okay? This is also a nice property, and it's called as space derivative. Okay? So now we will move on with some other properties. Okay, next step is to do the transform of derivatives. Okay? So here is an example. I have the derivative of f with respect to t, right? I want to find the Laplace transform of this. So this property or this concept is going to be used a lot in solving differential equations in physics and engineering problems. So it is really crucial. This is probably the most important of all the properties of Laplace transform for us. So we will see how it works. Okay, the Laplace transform of df over dt is simply given as this. Here I have df over dt, okay? So I want to make it f, right? So we are going to be doing again integration by parts. So I want to make this df over dt f, right? So that's why I'm going to call dv as df over dt. So v is equal to f of t. This is simple. So u, I'm going to call u as the other, what's left is u, e to the minus st. So du would be equal to minus s e to the minus st dt. Okay? So this integral becomes u times v e to the minus st times is f of t into 0, okay, minus v du. So u, there's a plus s here, e to the minus st f of t dt. Well, this is great. This term is nothing but f of s, right? Okay. So when this t goes to infinity, the upper limit, this term will be 0. When t is equal to 0, this is 1, and this is like f of 0. So it's going to be f of 0 positive. So you usually see this positive symbol here, and there is a minus, because that was the lower limit of the integral, right? So 0 plus means you go to 0, time is equal to 0 from the positive side, right? So f of 0 plus is my initial condition actually, right? So SFS minus f of 0 plus. Okay. Similarly, we can do the second derivative. Let's do that. And then we will write down a general relation. Okay. So I'm going to do d square dt square. Okay. So integral from 0 to infinity. I'm going to be a little bit careful here. T square dt. Okay. So here dv is going to be equal to d square f over dt square dt. So v becomes df over dt, right? Good. And then u becomes again e to the minus st. du is equal to minus s e to the minus st. Good. So this integral becomes from 0 to next part. So u times v, right? So u is that e to the minus st df over dt. So the limits are 0 and infinite. Minus v du, I have one s here, s integral, right, 0 to infinity, e to the minus st df over dt dt. First of all, I already know what this is, right? I already solved it before. As you may remember, this was S Fs, right, minus f of 0 plus. Okay. How about this one? So when t goes to infinity, this is 0. When t goes to 0, this is 1, and this is the derivative of f at t is equal to 0. So this is nothing but f prime 0 plus with a minus sign, because this was the lower limit, right? Plus. So in the end, what I'm going to have is s square f of s, right, minus s times f of 0 plus minus, say, df over dt when t is 0 plus. So we may continue like that, okay? We may give it a try for the third derivative and the fourth derivative. And in the end, what you're going to see is a general relation. So let's write that down. dn f dt to the power n, right? So it's going to be equal to, now, s to the n f of s. This is the first term, right? And then you start with minus s f of, this is n minus 1, okay? So you reduce the power by 1, f 0 plus, and then you start including the derivatives by reducing the power of s by 1 factor, okay? And you're going to get all the powers like that, n minus 2, okay? So f prime 0 plus, okay? Dot, 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 and the last term would be equal to d n minus 1 over dt n minus 1. So this is f, calculated at t is equal to 0 plus. Okay. So there is a nicer way to put it. So the Laplacian of dnf over dtn simply equal to s to the n f of s minus, you can use the sum symbol, summation, k runs from 1 to n. I have s to the power n minus k, right? And then I can have the derivatives k minus 1 f over dt k minus 1. All these derivatives are calculated at 0 plus. And this is the general relation for the transform of the derivatives. And this is really useful in solving differential equations. We will see that later in some other videos. Okay? So let's move on. There are a few more properties and then we are going to finish. Okay, next we will discuss S-space integration. What do we mean by that? So we have a Laplace transform of a function, okay? Sigma is my frequency variable here. So I'm going to integrate it from s to infinity. So let's use the definition of f. So it's going to be equal to from 0 to infinity e to the minus sigma t. I have a function f of t dt. And then there is d sigma. At this point, I'm going to assume that it's possible to switch the order of integration. I strongly suggest that you go ahead and read about the conditions when we can do that, okay? So I just assume that it's possible to change the order, okay? So if I can do that, this gives me, the time integral is going to be out, so I can bring f of t here. So I'm going to do the sigma integral first. So this gives me e to the minus sigma t d sigma, right? So the integral from s to infinity, then I have dt. So it's going to be equal to integral from 0 to infinity, I have f of t, and then when I integrate it with respect to sigma, I'll have minus 1 over t e to the minus sigma t. The limits are from s to infinity, and I still have dt here. Okay, so what does this term give me? So when t goes to infinity, this is 0. The lower limit, I put sigma to be s. So here the sigma goes to infinity because I did sigma integral, right? So when sigma goes to infinity, this is 0. When sigma goes to s, it's going to be, since this is the lower limit, I'm going to get minus 1 over t minus st. So the limits are gone. This is dt. But this is nothing but e to the minus st times ft over t. So this is the Laplace transform of f over t, right? So this is nothing but the Laplace transform of f of t over t. So this is the property of S space integration. This integral gives the Laplace transform of f of t over t. Okay. So now next step is to do the t space integration and see what it gives us. So I'm done with the S space integration. So now I'm gonna discuss what t space integration mean within the context of Laplace transform. So the main idea is to find the Laplace transform of the integral from 0 to t f of tau d tau. So this is still a function of time t, but t here is the upper limit of this integral. So from the definition of the Laplace transform, this is e to the minus st times the integral from 0 to t f of tau d tau, then dt. Good. Like as I did before for S-space integration, I'm going to assume that changing the order of integration is possible for the given integrants here. And the main problem here is there is t here, right? So this is one of the integration variables, okay, for dt integral. So we need to be really careful then. If I look at the tau and t space, so I have d tau and dt. In this form, I'm actually taking one time t, okay, and this also makes the upper limit here. So let's pick this time here, t, and I'm going to choose a differential dt here. So this is dt. For a given time t, what I do here is I run tau from 0 to t. Okay? So the tau, in the tau direction, I'm simply integrating over that region here. So this is t. So this is the line tau is equal to t line. Okay? So then I change my t, so t runs from 0 to infinity. So basically I'm actually integrating in this region. Okay? When I switch the integrals, like the order of integration here, then I'm gonna do my t integral first, okay, for a given tau value. So I'll be still in this region. Then what I need to do is, I hope you remember all these from your calculus class. It's just going to be a review. So for a given tau, so let's say I pick here. Okay. And this is d tau, right? Taking a strip like that. So for the t integral, okay, the values of t, so this value is also tau, right? So the lower limit for t becomes tau, and it runs all the way to infinity. Okay? So when I switch this order, what I get is the integral. So this time, tau is going to run from 0 to infinity, right? And then I have the t integral, which runs from tau to infinity. So this is how I should define the limits for the t integral. So I have e to the minus st f tau dt d tau. Okay? So the first integral is over t, so I can put d tau out. So this is f tau here, f tau, and this is dt d tau. So I'm basically doing the t integral first. Okay, I hope it's clear. When I do that, this gives me e to the minus st. The integral of that is, so let me put the other one first, f tau. Okay, so the integral of that with respect to t is minus 1 over s e to the minus st. So the limits are from tau to infinity. And then I still have d tau. Okay, this is good. I can move from here. So when I look at these limits here, so when t goes to infinity, this is just 0. The lower limit just gives me, this becomes plus 1 over s, and this becomes minus s tau and d tau. Okay. This is simply equal to 1 over s. I can take s out. The integral from 0 to infinity. So f tau, right? Or maybe I should put e to the minus s tau, f tau, d tau. But this is nothing but the Laplace transform of f of t, right? Or in other words, this is f of s. So basically, the Laplace transform of this integral is equal to 1 over s times fs. Okay, so we are almost done. I actually want to mention two other theorems, and then we are going to solve maybe a problem and see how we apply Laplace transform. So now we are going to talk about the initial value theorem. Okay, so we will use the Laplace transform of df over dt. So this is something we learned before. So this was equal to s f of s minus f 0 plus. Okay, this comes over from here. Okay, the Laplace transform of the derivative. So we are looking at the Laplace transform of the first derivative. We assume it exists. Okay. So let's use the definition of Laplace transform here. So this is nothing but 0 to infinity e to the minus st df over dt. So dt, which is equal to s fs minus f 0 plus. Okay. So here at this point, what I'm going to do is I'm going to take the limit when s goes to infinity. Okay. And see what happens. So when s goes to infinity, this integral becomes 0 for any value for t, right? So if I take s to infinity, okay, e to the minus st goes to 0. So this integral, the value of this integral approaches 0. Okay, so then 0 must be equal to limit when s goes to infinity s f of s minus, well, this is the initial value of the function, right? It doesn't have any s in it, so it's just a constant f0 plus. Okay, so then I can simply say that I dropped the razor. So I can simply say that limit s goes to infinity s fs is equal to the initial value of the function. And this is called the initial value theorem. Okay? So now we are going to discuss the final value theorem. And it's going to be our last discussion on Laplace transform. And we are going to solve a problem. Now we will talk about the final value theorem. So I'll be using the same Laplace transform as f of s minus f0 plus. Okay? The definition of Laplace transform gives me 0 to infinity e to the minus st df over dt, which is equal to s f of s minus f0 plus. Okay, so at this point I'm going to take the other limit. So limit when s goes to 0. Okay. When I do that, what this gives me is that the integral here from 0 to infinity, df over dt, because e to the 0 is 1. Okay. So this is equal to limit. I cannot put 0 here because f of s may have poles, right? May have stuff like 1 over s squared, right? I don't know how it looks like. So the limit when s goes to 0, this is just s f of s minus, so this is a constant, so I can just keep it as f0 plus. Okay, so let's look at this integral. This is nothing but f, right? df over dt integrate over dt. This just gives me f. The upper limit is infinite, lower limit is 0. So this is nothing but f infinity minus f0 plus. So f infinity means the value of the function when time goes to infinite, okay, or large values, okay. So that's why it's called the final value theorem, because initial values are gone. So the limit when s goes to 0, s of f of s is simply equal to f infinity. So put it that way. So this is equal to f infinity. Well, the problem is we cannot always use this theorem. The reason is f of s may not be defined for values of s close to 0 in some cases. One typical example is, let's say, Laplace transform of e to the kt. So it was 1 over s minus k, however, s has to be larger than k. So we cannot take s goes to 0 limit for this case, right? So the use of this limit is kind of limited, okay? But it's good to know. In some cases we may use it, but most of the time it is not as useful as this one, okay? Okay, this completes our discussion. Now I'm going to solve a problem using Laplace transform and see, you're going to see how it works. Okay, here is my example. I have a differential equation which says like the second derivative of x with respect to time plus a constant square omega square times x is equal to 0. So this is the equation of a simple harmonic oscillator. The initial conditions are given as when t is equal to 0, x is equal to x naught, okay? And dx over dt when t is equal to 0 is simply equal to 0, okay? So x here is the position of our system, okay? So in other words, this means that initially it's at rest, it's not moving, and it's at some point x naught with respect to x is equal to 0. So for this problem, x is equal to 0 is our equilibrium point. So we will learn all these stuff in our physics class, but for the time being, let's see this as a mathematical problem, pure mathematics, and we will try to solve this problem. Solving means we want to find x of t. Okay, so you want to solve this using Laplace transform method. Okay, so what we do is we basically take the Laplace transform of this equation. So this is nothing but Laplace transform of d square x dt square plus omega square, the Laplace transform of omega square is here, x, which is equal to 0. Okay. Okay, what is the Laplace transform of the derivative, right? So we're going to put 2 here. So this is nothing but s square. Let's say f of s is the Laplace transform of x. Okay, let's define it that way. I can define it here. So f of s is nothing but the Laplace transform of x. Okay. So s square f of s minus s times x initial minus dx over dt when t is equal to 0. Okay. Then I have plus, so this was the first term, omega square, then Laplace transform of x is f of s. So this whole thing is equal to 0. Okay? So at this point we put the initial conditions. This is the power of the Laplace transform. We don't wait till the end, okay? We just insert the initial conditions right away at the beginning. So this term is 0 because initially we are at rest, right? This term goes away. And this here is simply a constant x naught, okay? So let's write it down again. So if I take f of s terms, I have s squared plus omega squared, right? Then minus s times x naught, which is equal to 0. So f of s is simply given as x naught times s over s squared plus omega squared. Okay? So at this point what we do is we apply the inverse transform. Okay? So the inverse transform of f of s is simply x of t. Because the Laplace transform of x is f, the inverse transform of Laplace transform of f is simply x. Okay? So we go back to the t space. Okay? We first went to the s space from t space. We did some algebra, and then now we are going back to t space. So it's going to be equal to x naught is a constant, x naught, okay, times. So what is this thing? What is the inverse Laplace of s over s squared plus omega squared? Well, I see it over here, right? Okay, so the Laplace transform of cosine omega t is equal to s over s squared plus omega squared. So the inverse transform of this just gives me cosine omega t. So the answer is x naught cosine omega t. And this is my answer. And you see how powerful the method is. So we don't really need to know to solve like differential equations, right? If you know the Laplace transform, it actually helps us solve these type of differential equations with given initial conditions like that. So this is a really powerful method. So in other videos, I'm gonna solve some physics and engineering problems, a little bit more complicated ones, and we'll see how Laplace transform works in those cases. I hope you enjoyed the video. This is all for today. I actually prepared a summary sheet for you. It's just one page, and I'm gonna put the link to this summary sheet under the descriptions of the video, and it includes everything that we have discussed today. This is all for today. I hope you enjoyed it. I look forward to seeing you soon in other videos.